Welcome to Lesson 7. I'm Dan Olandisi, a science teacher, and I use OpenSciEd in my classroom. We've reached a point in Unit 2 where words like push and pull aren't quite enough anymore. Our students have built a solid qualitative model, but they are starting to ask questions that words can't answer. Questions like how strong or at what distance. So we are introducing the math not to just calculate, but to give us a language precise enough to describe what is actually happening in the storm cloud. In this video, we will trace that transition from observation to calculation, identify the key moments where the data modeling happens, and share the tips you need to manage this simulation effectively. So let's take a look at where we are coming from to set the context for this investigation. In Lesson 6, students figured out the mechanism of how charging occurs in a cloud by determining that collisions between ice and water separate charge to the top and the bottom of the system or the cloud, which was similar to what they saw in their sticky tape investigation. However, they also realized that there is a massive difference in scale. That gap leaves us wondering, how do variables like the amount of charge and distance affect strength of those forces? Here is a roadmap for this lesson. This is a 3-day investigation, and I want to be upfront. The prep time here is real, and I usually budget a solid 90 minutes to get everything ready because we are setting up sensitive scales and preparing materials that need to work reliably. That being said, the prep time does go down significantly after you do the lab the first time and you have some of your materials prepped, cut out, etc. We are doing a hands-on lab where students use digital scales to measure electrostatic force. This lesson also requires devices for the data analysis portion, as students will be inputting their data into a shared class spreadsheet. The data spreadsheet tutorial and computational model explanation are teacher-facing guides designed to help you master the simulation before you bring it to your students. I view this lesson as happening in 2 distinct sense-making loops across 3 days of instruction. In the first loop, we navigate from the storm context to a controlled lab setting. We investigate by collecting data on how distance and charge affect the force. From here, we figure out that as distance increases, electrostatic force decreases in a nonlinear way. But as charge increases, the force increases linearly. This leads us to wonder, how can we represent these relationships mathematically? In the second loop, parts 8 through 14, we move from the physical lab to the mathematical model in order to figure out that as distance increases, electrostatic force decreases in a nonlinear way, and as the amount of charge increases, the electrostatic force increases linearly. At its core, this lesson is when we discover Coulomb's law. I treat this as students earning the equation. We use the data they just collected to validate the formula. Then we pivot to applying that law to the lightning system. This is where they calculate the forces involved in a lightning strike and realize the immense scale difference, finding that the charge is 10,000 times greater than what they measured in the lab. It explains why lightning is so dangerous. We move past just saying opposites attract. Now we have a mathematical law, Coulomb's law, that quantifies that interaction. I emphasize 2 main takeaways here. First, the specific relationships in the equation that force increases linearly with charge but drops off exponentially with distance. And second, and most importantly for our unit story, the scale. We figure out that the physics governing our charged plates is exact same physics governing a thunderstorm. The difference isn't the rules, it's the numbers, specifically that massive 10,000-fold increase in charge that turns a spark into a strike. There are 5 specific instructional moments in this lesson that I pay close attention to. The first key moment happens right at the start when I demonstrate the digital scales. This is crucial because students are used to measuring mass and not force with this technology. I take the time here to show them that when I zero the scale with the setup on it, an upward pull, an attractive force, registers as a negative number. A downward push, a repulsion, registers as a positive number. I found that if I don't show this demonstration, they get confused by the negative signs later on in their data. And that brings us to part 5 and 6, the Coulomb's law investigation. This is where we divide and conquer to build our data set, testing like charges, opposite charges, and varying quantities of charge. Now, I want to be honest with you, this lab took me a couple of tries to feel comfortable with. It can be finicky, but here's the most important thing to remember. The experience and the observational knowledge are far more valuable than the numbers being perfect, even if the data is a little messy. If the students walk away seeing the general patterns, that force drops quickly with distance and grows with charge, the lesson is a success. I'll share the specific techniques that finally worked with me in the tips and tricks section coming up next. The next moment is when we analyze the class data. And this happens in part 7, where they encounter that nonlinear relationship I mentioned. I watch for students expecting a straight line and being puzzled by the curve. I validate that confusion. It's important that they recognize that this force behaves differently than others they might have graphed before. This steep drop off in force and as distance increases is evidence that we need to justify the r squared in the denominator of Coulomb's law later. I often refer to squaring the distance as a mathematical way to show it is more significant to the overall force we are measuring compared to the quantity of the charge. In part 8, we gather for a scientist circle to define Coulomb's law. I don't just put the formula on the board. I have them map their lab experience to the variables. I ask them what each of those variables represents, such as Q standing for charge of an object. I also tend to have them record these meanings in their personal glossaries. This is also where we discuss the constant K. I explain that K just handles the units, so everything equals out. It keeps the math from being a barrier to the conceptual physics that's happening. The final key moment is the calculation in part 12. This is the payoff. They use the equation to calculate the force of a lightning strike. When they see the results, force in thousands of newtons compared to the millinewtons they measured in class, it clicks. I make sure to pause here and let that number sink in. That factor of 10,000 difference in charge is what transforms a harmless spark into a deadly strike. It connects the math directly to the safety theme of the unit. We wrap up by acknowledging a loose thread. We have a great mathematical law for charged objects, but students will recall that in earlier tests, neutral objects were also attracted to charged ones. Coulomb's law, as we have defined it so far, doesn't explain that. This sets up perfectly for lesson 8, where we will investigate polarization to explain how neutral objects interact. So let's talk about logistics, because this lab can be tricky if the conditions are not right. Humidity is a real challenge here. If my room is over 40%, I run a dehumidifier. Because of that sensitivity, I always test the investigation myself before students arrive. If I can't get a good static charge, I know they won't be able to either. If the pink foam board isn't generating enough charge, I've had success switching to LDPE tubes in the photo here, but the biggest tip is this. Practice this lab yourself to get the technique down. And if you test it and the weather just isn't cooperating, don't feel bad. I give myself permission to switch the experience to a qualitative one. It is far better for the students to successfully observe the patterns of interaction than spend the entire period fighting for quantitative data that just isn't there. In my experience, the distance versus force data is usually reliable. Students almost always get that nice curved line of best fit. However, the quantity of charge data from stacking foam is much less consistent. It is very difficult to get perfectly doubled or tripled the charge live in the classroom. If the numbers don't line up, I treat the lab as a qualitative success as long as they see that more foam equals more force. The experience is valid. To ensure the analysis still works, I build on that experience by giving them backup data set I collected myself on a good day, and I keep this ready in case of emergency. This way, they get the hands-on practice, but we still have clean numbers to verify the math. And this brings us to the calculations in part 12. It's easy to get bogged down in the algebra here, but it's helpful to remember that getting the right answer is not the only target. The goal is for students to understand the equation as a model. We want them to see that math is just a predictive tool that describes the relationship they discovered in the simulation. That being said, it's also important for students to try the math, and to help them with that, I use strategic grouping to manage the range of math abilities in my classroom, and you can do the same. You can certainly use heterogeneous groups to mix abilities, but I actually prefer homogeneous groupings for this part. By grouping students with similar math comfort levels together, I can commit the majority of my time to supporting the groups that are struggling, while the more confident groups can move ahead independently. If you are in a co-taught setting, this is a prime opportunity for parallel teaching. Splitting the class to lower the student to teacher ratio makes a huge difference during those heavy calculations. Finally, I insist they show every intermediate step and unit. It's not busy work. It's the only way to catch those conversion errors between centimeters and meters before they derail the whole result. We have one major addition to our glossary in this lesson, which is Coulomb's law. I define this with the class as a relationship where force is proportional to the product of the charges and inversely proportional to the square of the distance. We might not write that whole sentence out, but I want them to have the formula and the definition of each of the variables in our model clearly noted, and hopefully good descriptors of what Coulomb's law means. There are a few posters to manage here, and I make sure to bring back that mathematical anchor chart from the polar ice unit if we have it, as it helps with graphing skills. We also create a new solving for force using Coulomb's law poster, and I treat that as a step-by-step anchor chart for the calculations they do in part 12. Finally, I save the computational spreadsheet results comparing like and opposite charges. We will want to refer back to those data trends later. And that's lesson 7. It's a heavy lift on prep and math, but it provides the quantitative backbone for the entire unit. In the next video, we will look at lesson 8, where we figure out how that charged cloud can interact with the neutral ground. Thank you for taking the time to learn lesson 7, and we hope you have a great experience in your classroom.